force to move by the sum of this wave and this wave. Well, that wave minus that wave. Okay? So by forcing the float by that amount and then restraining its motion, we're reducing the power that's put back into the wave on the right. Right? So it's so the power output is just the energy difference of the instant wave to the extracted wave. Right, so that's always our target. Getting a radiated wave cancels out the instant wave that exists without the device in place, and we get this problematic case of a radiated wave in the other direction, disrupting the flow. Okay, but that's not really that question. That's follow-up. Right, so that's concepts. I guess what's part two? Frequency-dependent heat excitation causes added mass for a cylindrical body with immersed volume of 5 metre radius and 8 metre shaft. Okay, so we need water. So those are the graphs at the bottom of the page. Estimate the amplitude of the wave-induced excitation force.
What's he talking about?
And do something with it. On this stage of the work, when the instant wave period is 10 seconds, amplitude is 1.5 metres. So this is basically just using the graphs for a given wave period. Right? So it's interpreting the graphs at the bottom of the page. So what do we interpret by these graphs? It's a graph of force, something like 0.5 hertz dropping down power, and this is minimum. This is left hand side anyway, and then we have same right hand side. Lucky that's a bit of chalk. Something like this. That's about 1.9 and that's about 1.1. Right, so we want information at wave period of 10 seconds. How do we use these graphs? It's just interpreting the graph, it's not really depending on the course. Right, so this is G, and this is a rho. So this is the same as just a set of data in the notes where we've got two graphs and a table above it. Right? But in that case we were looking at force and damping, whereas here we're looking at force and added mass. So we need different things. So the first part of the question, estimate the amplitude of the wave-induced excitation force on this stationary immersed volume when the instant wave period is 10 seconds and amplitude is 1.5 meters. So which graph are we using and how are we using it?
Force graph. You have to find the angular frequency first.
Right, so what's the angular frequency?
2 pi over 3x.
Right, so what's the angular frequency?
He's drawing like a tiny amount of power.
Over. Can we get that? Happy with that again. Right, so what do we get? So 0.628, somewhere over here, up to our point on the graph, across to here, straightforward, get a value. Right, so what does that give us as a value? After each graph, about 46, 45. Yeah?
Yeah, about 45.
Right. Text to the graph, caption to the graph explains, well, and this explains how to get that into real units. So how do we get that in newtons?
45. What? Is it 45? Yeah.
So here it's given as F3 over rho G, and the caption says it's called unit amplitude. So what is that in real units? In terms of newtons or kilonewtons or grams per seconds, meters per second squared. Which obviously isn't a very good unit. Pounds per foot squared. No, pounds per foot per second squared. we know F3 over, right, well, F3 over rho G is equal to that. F3 over rho G, and this is for a unit amplitude, so this is A, we could say, right, is equal to, what did we say, 0.5. So just rearrange, because this is non-dimensional, right, because rho G A takes out all units. So F3 is equal to 0.5 rho G 1.5, where 1.5 is our wave amplitude. Right? Fine. So value. Let's see that.
678 times 10 to the third
6, 7, 8.
times 10 to the third.
So kelvins. Right. So that's the amplitude of our excitation force, which we would expect we can approximate by our equation for Krylov, which is somewhere down there. Right, you've got that written in the paper. Before I break the blackboard turn. Right, so straightforward graph, one-dimensional units, convert into dimensional units, 678 kilograms. So what do we want to do with that? Well, it turns out not a whole lot. Part C, calculate the displacement mass and using an iterative method, estimate the added mass and natural period of this body. And later, calculate optimal power of the luminary. Right, that's a bit of abstraction. So we've done all we need with force for now. So how do we calculate the displacement mass? And how do we use an iterative method to estimate the added mass and natural period of this body? Must be complicated because it's got 7 numbers.
Can I ask something regarding the previous part?
Yep.
When by excitation force, what is meant in the floating point?
All of the forces corresponding to this. Right?
Yeah.
So it should be Frau Krylov plus scattered, which is diffracted. Right? But normally Frau Krylov is a good approximation. So we could write here F3 is equal to F diffraction. Right, which is equal to F scattered plus F Frau Krylov. Right, and all of that is approximated to F Frau Krylov on the bottom. And this approximation, that bit, is okay if D less than L on 5, where that's the weight. Right? And that's the diameter. So if the float is quite small, then this is okay. And that's okay because if the float is quite small, those velocities are quite small. That's the width of the float, the difference of velocities. Right? So excitation force is normally diffraction force, total diffraction force, and that should be the sum of scattered and Frau Krylov, but Frau Krylov is a reasonable approximation on its own in most of these cases, provided the float is small.
Is the diameter there the diameter of the object, the float? Or?
Yeah, so that's right. So diameter perhaps is a bit misleading, but characteristic dimension is what it should be. Right, so if it's a cylinder, it'll be the diameter. If it's a very long strip in the page, it'll be a bit rather than the diameter.
What's in front of it? Is that just a square? I don't know what that is. That's scattered. What's that part?
Right, so we've got this float. Get back to this diagram of this. Start. Yeah, we've got this float. It has a circular section on the plan, so it's like flat on the plan. It's circular. As you say, it's got a radius A, and that's the same as D. Right, circular on plan, and it's got a draft with something. What do you think the draft is? 8 metres. So 8 equals 4 metres. H draft equals 8 metres. Right, so this is from mean water line down, still water is 8 metres. Right, so in this case, when the float is oscillating, well, not actually in this case, when it's resonant oscillating, we can get its natural frequency. So that's what we're after in this case. So for any system with a mass and stiffness, we can get a natural frequency. How do we get a natural frequency of these floats? Well, what's the equation for getting the natural frequency of anything?
Root K over M.
Sorry?
Root K over M.
K over M. Yes, so what? F equals root K over M?
There's no omega.
Omega. Right. Omega is equal to root K over M. So that is the same as K is equal to M omega squared. But here we're not using K because K is a bit confusing. Because we have K the wave number. Right, so in hydrodynamics, so our K is actually here replaced with S. S for stiffness. Right, throughout this course. Right, so that's what we want. Omega N is equal to this. So how do we get each of those components? Expand for our case of a wave energy course. What, and you should know that one, it's from other courses, it's not from here. So, if we go through each term, what is omega? We know omega is natural frequency, that's what we're trying to get to. Fine. What is S then? How do we calculate S? What is the stiffness of our heaving float? Why does it have a stiffness? So stiffness is just a force proportional to displacement. So what is the force proportional to displacement?
What is it?
Right, so let's go back to this one. If we have our float here at time 0, right, and it has displacement of 8 metres, so that just goes down to that point. Right, what is the upward force on that float in still water? Okay. So float, still water, put it in this position to start with, as draft of 8 metres. So what is the buoyancy force on that float? I.e., what is the upwards force F? Buoyancy. How do we get buoyancy on an immersed object? Or partly immersed object?
The water is displaced.
The
The weight of water displaced.
weight of water displaced. Very good. Right, so how do we get the weight of water displaced? F buoy is equal to rho. Rho V. Just rho V. Weight of water displaced. Rho V T. Right. Where V is the volume of the float. So this area in this case is V. Right, and V is just a cylinder, so pi a squared h for the float volume. Okay, fine. So what is the change of buoyancy force per change of immersion? So this is our displacement. If we were to increase the displacement by 1 metre, how does the buoyancy force change? Plus 1 metre.
Proportionally
2
to the depth.
So just what here? Proportional to the depth.
V.
So how can we write that? So if the volume is pi a squared h, what is the stiffness term for each unit change in h? If you write it out in full. So that top equation we can equivalently write rho g pi a squared h right?
So rho pi.
So if we were to write the force as a function of immersion, or sorry, change of immersion, right? How do we change that?
So
Which part of that is the force
so
per
H and E.
increment of immersion?
Rho g pi a squared.
Right, so we just change that to 1 for our case. So that bit is actually S, right? Because all of this exists to start with, but it's just cancelling out the displacement, sorry, the sinking of the float. So the float's got that mass because it's floating. So rho g pi a squared h doesn't really matter because it just cancels out its buoyancy. Right? So what does matter is how it changes when we increase or decrease s by small amounts. So that actually goes to s, right? And then we have that times z, wherever it is, our up and down motion. So our force, our spring term is s rho g pi a squared. So pi a squared is the water plane area. Right? So our spring force then evaporates. Okay, so we've got s just there, over there. Well, sorry, we only really want that, don't we? S. S is equal to m squared. Alright, so good. So we've got rho g pi a squared is equal to m and squared. So what's m?
Mass
Which mass?
of the float.
Of the float. Yeah, okay, so displacement mass of the float, right? But is it anything else as well? So m, for that we know that is that. Fine.
Is the force along the
What about m? M, you are presently saying is just rho v. Yeah? Rho v equals rho pi a squared. And this is where h does come in because we've actually got to support the mass of the float. Right, is that it? Is that the only part of the force? Is that the only part of the force that's in phase with acceleration?
F rad.
Well, not all of it. Which bit of it?
The velocity man.
Which bit of that is mass?
Acceleration.
The
E3.
Not damping part.
not damping part. The added mass part.
Yeah.
All in the name. Added mass. Right, so rho v is equal to our displacement. Right, okay.
Has he got any options next year?
And then we've got our other part, which is our added mass part. So m is equal to rho v plus a 3. And they've both got to be in units of kilograms. Plus that bit. I've got part 1, right, part 2. So plug those into our expression for stiffness equal to m over squared and evaluate accordingly for omega n. Right? And you should have to run through that quite straightforwardly, but clearly we're going to need this graph to get our value of A3. So, you probably want to work through that.
What is basically the term added mass? What does it indicate?
What does it indicate? This.
No, the added mass.
Yeah, but that's what it indicates. It indicates a component of the radiation damping force. Right? So, a component of a force that is required to generate a unit velocity wave. That's it. In this case. In other parts of the course, you'll probably have added mass as the part of the force required to change the inertial streamline. Something like that. Or the amount of additional fluid that has to be moved with the mass of the float. Right? So it's not really attached. It's not the same amount of fluid that's attached all the time, so that's a slightly misleading one in this case. So here, mathematically, it is the component of the force that is in phase with acceleration when you're generating a unit amplitude wave. Right? And it ranges a bit in frequency, as we'll see it later. Okay, so, that's all a bit of a scribble, but evaluate those then. So we've got rho g pi a squared, so what is our value of s? Any numbers?
It's A.
8.
25. 789, 780, 790.
We need those, and then we can get.
That's just 789.7 kilonewtons per meter.
789 point.
7 kilonewtons per meter. And is that right?
Right.
Right.
What did you put for alpha?
5, wasn't it?
No,
Is that
it's
right?
1.5.
Is it?
Isn't it?
Alright.
Alpha is
Small.
the amplitude.
Oh yeah,
Right.
Oh, sorry, the radius, yeah.
Right.
that was right, yeah?
You got it.
Oh my god.
Like you're using the wave amplitude. Right. Yeah. Yeah. So in past papers there is a bit of confusion between A and alpha. So it should be clear in the words, but the notation probably been clarified to be. It should be A is the radius rather than A is the wave amplitude. But in a couple of cases in old papers and old questions, there might well be A is equal to wave amplitude. So that's just
Rho V is 644 times 10 to the 3.
okay. And A3 only get in.
Only get N.
So this needs to be at the frequency of oscillation. A3 only get in.
Would you get it?
255.
255. So how do you get that?
I'd have to divide by density first, right? I just got the number from the graph.
Okay. So how do you get that number from the graph? What frequency does that come from?
The frequency for a period of 10 seconds.
Okay. So how do we know that omega n is 10 seconds?
No, omega n is the frequency due to a period of 10 seconds.
Okay. So O3 2 pi on 10
Yeah.
is equal to, what is it? 255.
Yeah, 255.
255, and then we've got to dimensionalise that because we've got
Yeah.
so 255 times what? Especially times 1 over 25 equals whatever it does.
Should we divide?
Okay?
Shouldn't you divide it by
Divide
rho?
it.
No, the graph is given as A3 divided by rho, and you want A3.
Oh,
Oh, yeah.
Right? So that's for a frequency, but you don't know that that's the natural frequency. So that on our graph is here. Yeah? Where that is 0.628. And that one was 0.628. So that's fine. That's a start, but we don't know that that's actually what this value is at the frequency of interest. So let's start there and work through. So that's basically what, 260,000, with very slight adjustments, call it 260, it doesn't really matter now, times 10 to the minute. Right, so from all that, you can get your value of omega n, because you now know A3 at an estimated value of omega, rho v, which is your m term, so sum lift, and s. So continue.
Iterate.
Okay, come on then.
Iterate the A value.
Betray the A value.
Iterate.
Alright. Betray the A value. Wow. I'm going to iterate.
Oh my god, what's that? Can't you?
That's a bit strange. No, there's no iterative formula there. There's no iterative formula there.
There is.
How do you get 255? For A naught. Oh, right. How do you get 255 from the graph?
I'm not sure.
Right?
Wait,
Well,
he went up to the thing.
Okay.
You got 255 from the graph.
He went at 0.628 after you went to
Oh,
the
that's
period
adding
10
mass.
seconds. You got here 0.628 from there. And then you went up from 0.628 there to get 45.
Okay, 9.628 is the...
Yeah, it's that frequency if you do for a period of 10 seconds. If you use the equation.
so, when is it on again? Or better still, Tm, which is what we're after.
The mass is added, right? Not taking away the 255 times 1025.
Yep.
100.
255 times 1025 added on to our 644 times 1000. So, 644 plus 205 times 10 to the 3 is fine. Yeah.
No 0.934.
Sorry?
0.934.
0.934.
Is that right?
Okay. 0.934 rad per second. Okay, so we have a first, or actually second now, estimate of the natural frequency of the system, or natural angular frequency at least. So where does that sit then on our graph? And is that right? So the only assumption we've now made is that A3 is obtained for a period of 10 seconds, i.e. an angular frequency of 0.628. So this is for a different angular frequency to this. So this is actually a little bit different from what we assumed. Right?
0.23.
Yeah.
Okay, nice.
0.9.
So we're actually
No,
somewhere here.
no, it's not complete.
220, 228.
Right, so how does that change
27.
things?
227. A3 over rho is 230, 227.
227 or 230. Yep, okay. So that's actually out by, what does that make it? 25 tonnes, almost 30 tonnes. Quite substantial. Change for small change. Alright, so you look at a massive effect on our period because it's only a 10% change of something that's only half the mass anyway, so it's only about a 5% change of mass. But it does change this a little bit. So recalculated our new case to get a final value.
Would it be alright just to say that it's not that big of a change to the mass, and then therefore you could iterate more, and then leave it at that?
Well, I'll leave out the calculation.
Yeah, the omega n.
Probably as quick as do the calculation.
Because then you have to